And the pressure of oxygen in a 19.1 liter flask is 553 millimeters of mercury at 57 degrees Celsius. What is the mass of oxygen in grams? So what we will see is that when you're talking about gases and when you're talking about grams or moles, there's only one equation that you need. It is the ideal gas law, and it is PV equals nRT. And for this example, there's only one gas, it's oxygen. So you can use the ideal gas law just as written. Sometimes we will personalize it specifically for oxygen, but it doesn't change the calculations at all. The only time this version can be better is if there's a mixture of gases. And we would call this the partial pressure of oxygen. But since there's only one gas, either of these versions works fine. From there, we see, we're asked for the mass of oxygen in grams. So we're going to have to solve for the moles and then use the molar mass to convert into grams. I see that we have a pressure. Well, let's start here. So R, which is the ideal gas law constant, is 0.08206 liter atmospheres per mole Kelvin. And so what that set of units means is that whatever volume I have must be in liters, whatever pressure I have must be in atmospheres, moles, and whatever temperature I have must be in Kelvin. And so we often run into a lot of unit conversion issues with this. So I have liters in my problem statement. I do not have atmospheres, I have millimeters of mercury. And just like I said in the last video, that I'm oftentimes asked to convert from millimeters of mercury to atmospheres. Let's do that one first. 553 millimeters of mercury is my number from the problem statement. On the conversion and equation sheet, it says 1 atmosphere equals 760 millimeters of mercury. And so I can do my math to get my atmospheres. Oop, something right there. .728 atmospheres. While I'm here, I know that I need Kelvin, so I might as well do my conversion from degrees Celsius into Kelvin. Kelvin equals degrees Celsius plus 273. And 57 plus 273. 330 Kelvin. All right, I think I'm ready to start plugging stuff in. For these kinds of problems, there are two ways to do it. I do both ways sometimes. And they're both mathematically the same. One way is to put all the numbers in and then solve for the moles of oxygen. And another way, and I'll do the other way because I think, so the other way is to actually solve with the letters, symbolically is what it's called, for my moles of oxygen. If I get moles of oxygen, it's going to be PV divided by RT. And then I can plug in all my numbers here. Again, you can also plug in all the numbers and then solve numerically. But now I have my partial pressure of my oxygen. my volume given in the problem in the proper set of units, 19.1 liters. I have my R value, and our R value, just a side note, has 4 significant figures, and that's so it has one more significant figure than almost all the numbers in our problems. Plus my Kelvin temperature. And if I multiply this all out, 0.728 times 19.1 divided by 0.08206 divided by 330, I get 0.513 moles of oxygen. And we're not done yet because, of course, we've been asked for grams of oxygen here. But that's not the new part for this problem. That's something hopefully we're very comfortable with, but we still have to do. 1 mole of O2, oxygen, is 32 grams of O2. And let's do that last step. I get 16.4 grams of O2. Any questions about that?